Welcome to Talkless Water, the podcast that takes a deep dive into the world of water with those making waves. My name is Todd Bottler, and I'm host of Talkless Water. I'm also the principal of Collaborative Water Resolution, which you can find at waterdisputes.org. In addition, I'm editor-in-chief of the Texas Water Journal and Texas with Water. Both publications are free. My guest today is James Perry. James is the Executive Vice President of ASTERRA. James spent over 30 years driving disruptive innovation. In both startups and Fortune 500 companies, James' key mission has been market adoption and to achieve a deeper foothold into new markets. James, welcome and thank you for being part of Talkless Water.
Well, hello, Todd. Thank you so much for having me today.
So let's start out with your background in water. Since this is a podcast about water, I always like to find out how my guests first became interested in water. So when was it that you realized that water was something that you were going to spend at least part of your time on in the future?
Yeah, it started for me about 8 years ago. I had spent about 16 years at Hewlett-Packard, and part of my motivations and what really gets me excited in my business life is to look for innovation and to find markets or new adoption of the innovation in businesses around the world. And part of that had me visiting Israel quite a bit. And Israel is known as Startup Nation. A number of innovative ideas come directly out of Israel. When I saw the power of this remote sensing technology that was able to detect water below ground, as you can well imagine, I was excited to look for ways to have this technology adopted in markets and utilities around the world.
So tell us how you're making that available to utilities and others around the world. Tell us about ASTERRA.
So about ASTERRA is a company founded in 2010, and our chief technology officer and co-founder, Loren Guy, was part of a NASA grant looking for water on Venus and particularly Mars, noting that water would, if it existed, would be below ground on Mars. You need to use very particular type of remote sensing. And once Loren had achieved that capability, he looked for unique ways on Earth to be able to adopt this technology.
So I love that. So I'm very interested in space exploration and what NASA's doing. So it sounds like your technology might have been the technology that was used to identify these lakes, which are under the Martian polar ice caps. I think there's a big one maybe that's been discovered that's under the northern polar ice cap. Am I right about that?
You're absolutely right. It really starts with planetary observation and satellites that give you the ability to look at very large swaths of land. In our case, it's about 1,400 square miles with any one image. And using microwave radar, in very particular wavelengths of that radar, we're able to penetrate through atmospheric conditions and penetrate through soil to reflect off of the signature of water.
So that technology, so how far down underneath the surface can you go? And does it make make a difference, what type of surface or stratigraphy you're looking through? For example, can you look through limestone and igneous rock, or can you only look to a certain depth?
Yeah, the capabilities of what is L-band in the microwave spectrum, and using synthetic aperture radar, or what we call SAR, we're able to penetrate between 1 to 3 meters, a depth of about 10 feet. There is certainly the capability to go slightly deeper, depending on the soil type. Sandy soils has a lot of penetration capabilities versus clays or granites. Generally speaking, we're able to get down roughly 10 feet before we reflect off of soil moisture.
So one of the things that's really interested me about your technology is apparently you can use it to find leaking underground pipes. And if anyone who's listened to this podcast before knows, I'm really interested in water infrastructure, and repairing our leaking pipes is, one of the things that is an easy way for us to stretch our water supply. And so, obviously right now we've got a lot of money to do that, or we've got more money than we've had in the past. Let's put it that way, with the Bipartisan Infrastructure Act. And so, do you have this technology that was used to define the underground lake on Mars? Do you have this on one satellite, or is it more satellites that are orbiting Earth? How's that work?
Yeah, so the capture platform for us, generally speaking, although we do some on airborne or on the bottom of airplanes, most of what we're doing is satellite based on Earth observation capabilities. And these 6,000 to 7,000 satellites that rotate in either a polar or a fixed orbit around the Earth are really reporting information. And for us, there are several different platforms, one through JAXA, which is the Japanese Space Agency, and another through SAOCOM, which is Argentinian and Italian group. We have a bank of 3 right now that we have certified and qualified for our needs. And they are active sensors, L-band, that are sending a signal and receiving a signal in a quad pole design, meaning 4 antenna, if you will, or images that come to us. And then we analyze those images. There's other satellites going up in the months and years to come that we will be able to use. But for our purposes right now, the 3 that we're using are highly trustworthy, if you will, good quality images. And that allows us to be able to analyze those images.
So, kind of give us an example. I'm a water utility, and I know I've got leaks in my system, and I'm trying to, I guess, prioritize where I'm going to put money to try to patch those leaks up. What would you do for me?
Well, this is the exciting thing about what we're doing on the analytics of the images, because the NASA grant was to look for water, soil moisture. Now, marry that, if you will, to our co-founder. His first job was working in Israel at a water company. And of course, Israel, which is essentially a desert, has a limited amount of available water. So every drop is precious. And so for the water agency that he was working at, they were looking for ways to determine where leakage was occurring. So Loren used as control points flooding his parents' backyard with a garden hose and using that as a control point for images as the satellites would pass over. But what he was able to do was to take the power of radar, and L-band specifically, which is highly sensitive to the dielectric constant of water. And the dielectric constant essentially is testing the conductivity of that moisture type. And he developed over about a 5-year period an algorithm that could look at the frequency of that dielectric constant and noticed and matched it to the additives that are in drinking water, like chlorines or fluorides. So he could then differentiate between all soil moisture, the signature of drinking water below ground. The premise being that if we're seeing it, we're not seeing a pipe, we're agnostic to the pipe, whether it's a metal or a plastic. But when that pipe is leaking, the only reason that we would see it is because there is a void in that pipe. Our premise is that we could report that information to the utilities and they could more actively see what you can't see at the surface, which is this pipe leaking below ground.
So it detects the water quality. So if I understand that correctly, that it's detecting water that's been treated to drinking water standards, and you can tell the utility, hey, there's a pool of it here where there shouldn't be, and then they go out and they look for a leak, right?
That's exactly right, and we just recently announced our 100th thousand leak found in the world. So it tells you that we ground truthed everything. We've been into the field 120,000 times to prove what we said was occurring below ground. Most of these leaks are not surfacing. AWWA estimates that any leak below ground will leak for 18 months before it ever surfaces, unless it's a catastrophic break. And the only way to be able to determine where leaks are occurring in pipes is to use a different form of sensor and try and pinpoint those. But it's essentially looking for a needle in a haystack. You're blindly going through your entire pipe system trying to find a leak. And what we're doing is guiding those traditional methods to a much more digital, if you will, approach to finding these leaks. And we've proven that we're finding 4 times the amount of leaks versus traditional or analog methodology. So the more leaks we're finding, the more water that's recovered and used for its intended purpose.
So, I'm looking at your data, and you're able to tell the utility, hey, this water is within so many feet of a certain. I mean, how accurate can you get in terms of like pinpointing the location?
Right.
Of where the water is and where their pipes are and all that.
Yeah, there are technical factors, and there's also the physics of how a leak is going to occur and where the plume will settle, if you will. And we get roughly into about 150-foot zone, so that and what we'll do as part of our value proposition is we overlay the pipe layers for the utility, and this area where we're seeing it will intersect what we're seeing below ground with where the pipe's occurring. And that allows you, when you go into the field, to be able to pinpoint within our 150-foot buffer zone, if you will, where this leak is occurring.
Oh, that sounds pretty neat. So would you, for example, a small town comes to you, their utility is, knows that they've got a lot of leaks. Do you produce an image that shows the entire area and almost kind of like hotspots or whatever, here leaks here, and they can look at it that way, or do you have to really kind of focus on, much smaller specific area one at a time?
Well, that's the power of what we have for about 1,400 square miles on imagery. Roughly speaking, there's usually about anywhere from 18 to 30 water utilities within that image. And so we'll task the satellite once contracted. It's basically a license that you have for a year period of time. And we will report what we're seeing below ground. And we do that through an Earth observation website that we have. You're able to log in and download it. It's compatible with Esri systems. And we also have the ability to show it on maps once we've overlaid those pipes. And that allows you to go into the field and use tablets or your computer to actually pinpoint live what you're finding and report that back through your operational teams.
So can you use this technology also to locate groundwater and measure the volume of groundwater on aquifers, anything like that?
Yeah, that's the exciting thing. As soon as we started reporting and we demonstrated significant successes, with water utilities, we are also being asked to adjust our algorithm for wastewater. So because of the additives and the different formulations within drinking water, wastewater, and reclaimed water, we're able to differentiate all of those and updated our algorithms. And after that, we were finding with these infrastructure stresses, aging infrastructure that's breaking down, you can't afford to just replace all infrastructure. We found other locations that were requesting general soil moisture mapping, if you will. As an example, earthen dams and levees are aging. They're intended to live 50 years, and they're now 75, 100 years old, and quite a few of them are being breached or failing or need repair and maintenance. And because of our technological capabilities, we can report all soil moisture maps below ground, again, within the depth and boundaries I talked about, 1 to 3 meters. But we'll see those first indications of piping or failure on a dam or levee, and that helps augment traditional methods, which are generally visual inspection and or some level of sensors. But we're giving a greater resolution, actively monitoring over time to, again, guide engineering or operations and maintenance teams to areas that are at higher risk of dramatic failure. We've also done it for the rail industry on trying to keep ballast and trains running at full capacity and full speed, where there's maybe landslides and slippage that are occurring. We're able to make sure that drainage is well maintained for the health of the ballast, and as well high risk areas for landslides that could cause dramatic train derailments and alike. Those are just a few examples of where we started to migrate from our what we call recover or drinking water leakage solutions into our earthworks, what we call earthwork solutions for risk mitigation on infrastructure failure.
So your dam example, well, that's a real issue here in Texas. I mean, we have a lot of dams, and the staff of the state agency, Texas Commission on Environmental Quality, that goes out and checks these dams. They have a huge workload. Let's put it that way.
Right.
And so I'm kind of wondering. I mean, it sounds like somebody who's got that kind of responsibility could use this technology maybe to look at specific dams and if they could detect piping or something, well, obviously, they could prioritize which dams they need to go out and physically check and recommend for repair or something.
Well, Todd, you're absolutely right. In a couple of examples, we've had great success in the great state of Texas by adopting innovation and our technology through partners. We have multiple partners, the Maverick team, which is based in Austin, is helpful at getting us introduced to these new applications. We've taken a good long look at the Louisville Dam on the Trinity River, which is holding back water and drinking water. It's quite an older dam that needs a lot of maintenance and repair work done on it. So we could take a look at that. Or Collins County has 65 different dams, some for flood control, some for drinking water reservoir. And we're able to, with one image, again, that 1,400 square miles, we're able to look at multiple earthen dams within that image. And what we do to the various agencies is exactly what you said, is give them a more efficient play on where to go look, rather than only looking at a dam or a levee once a year or once 5 years. We're able to more actively monitor them with greater frequency to start to see areas of risk to go operationally get into the field and more effectively manage these significant resources.
Well, that sounds like a real advantage for the agencies that have to do that, given how many dams there are. I mean, that's always the big question: is which ones do you go look at, and what can you really tell by looking at them just, from the surface. And so I could see how that's it's an important technology for that. What, something else that comes to mind, in Texas now, we've got a lot of discussion about zombie wells. I don't know if you've heard of that term before, but these oil and gas wells that aren't properly plugged. And, you've got, a lot of nasty stuff coming out of them and potentially contaminating groundwater in layers, above or below those wells, or, even contaminating surface water. It seems like, your technology might be useful in identifying those.
We certainly have the capability of doing that, Todd. The challenges for all of it are great, and you're absolutely right that this infrastructure is key. We've been contracted for multiple years with San Antonio Water, SAWS, if you will, and sitting on one of the U.S.'s largest aquifers. They're concerned about the overall health of these aquifers. That includes any potential contaminants that would be a challenge, or that they're actively refreshed. And our ability to give moisture maps allows you to either overlay an asset, could be where these wells are occurred, and we could look for plumes, if you will, of moisture around those, which could be a key indication of where problems could occur, and or the overall health of groundwater, ensuring that it's seeping back into these aquifers in a healthy manner.
That's really interesting. So, I've spent a lot of time working with saws over the years, and the Edwards. Hadn't really thought about that application. Looking at water quality issues in the Edwards. See, there's a common misconception that karst aquifers, but in part because the Edwards water is so good, that karst aquifers are really good for removing contaminants from groundwater. It's not really. It's the opposite. Sand aquifers are much better than that, but for that purpose. But it's interesting. I hadn't thought about that. Any other water-related applications for your technology?
Oh, there's quite a few. In some of these, you wouldn't think of off the top of your head, but overall health of roads or even large parking lots, let's say for AT&T Stadium or all of the various stadiums anywhere in the world, you have very large parking lots. The asphalt is designed to last 25 years. And you don't want to see it fail early, not to mention sinkholes that could occur, but the overall health of that before you get that crocodile skin and it starts to fail, you get water seepage in there and potholes. What we're able to do is look for moisture below asphalt and to be able to report those as, a key early indication of where failure is likely to occur. And when you have these massive areas that you can only visually inspect, or you have to very aggressively dig or pothole, if you will, and then go into the effort of measuring the moisture in a lab, we're able to report that and actively monitor that over time. So whether it's parking lots, large Walmart or Prologis distribution centers, these really need to be maintained. Same with roads. As we're redoing roads, generally speaking, you need to know the moisture below ground as you're designing and then or maintaining these structures. And we're a data layer that gives a significant piece and resolution or information on that. So you see us start to get into rail, roads, earthen dams, levees, and alike, with a key piece of information that humanity has never had before. And our job is to work to have it be adopted to manage our aging infrastructure and our precious resources.
X-ray vision. You remember the comic books, from years ago, there's always X-ray vision, or it was like one of the superpowers or something. That's kind of like what you've got there, isn't it?
It's the closest thing I am to a superhero.
Well, before we wrap up, I've got, one question, then our final question. And so my next question is, so if I get, I've contracted with you and I get, I guess, a file that I can download on my computer and then can kind of zoom in and investigate the areas where you're finding water, drinking water, for example, if I'm a utility looking for leaks.
Yeah, that's exactly correct. We have a website that's password protected, built specifically for the utility or the partner or the engineering firm that we're contracted with. And what you have is the ability to view it and use it within our system, or download it as a flat file or shape file and import it into Esri or any other systems that you have that you're using to either work on design build modeling or in operational maintenance in the field.
GIS. Well, I would imagine that if you're a city and you're going through a drought and you're having a lot of leaks, which the soil starts to contract, right? When you get in the drought and kind of creates more leaks, that this would be something that would be very helpful in trying to keep ahead of that issue.
Yeah, that's right. And what we have found time and time again, independent studies that show the cost of the water that we're recovering, because that water is not going through their meter. And so the public utility spent a great deal of effort and resources to find it, to treat it, and to push it with greenhouse gases concerns off of electric. What we're able to do is have a very good ROI. Usually within a few months, the cost of our services is offset by the amount of water that is now being used. So it's a bit of a no-brainer for the utilities to be able to adopt it on the leak detection side.
Right. New water supplies cost a lot, and they're often hard to obtain because other people trying to go out and get new water supplies as well, and it usually means multiple entities trying to compete for the same source. So, James, one final question: how can our listeners find out more about ASTERRA?
Well, we have a very powerful website that you can go to, certainly, www.asterra.io. And we have resources, case studies, white papers that describe what we do. And there's an inquiry, sales inquiry, if you want to get a hold of us. I can be reached at james@asterra.io. And happy to share more information based on the multiple applications on which synthetic aperture radar is being used today.
And ASTERRA is ASTERRA.
That's right.
So just want to make sure our listeners know that when they're going to be emailing you or looking for your website. So, James, I really enjoyed this. Thank you for joining us today. I've learned a lot.
Well, thank you, Todd. And truly what you're bringing to the market are new ways of thinking about humanity, water topics, water issues. And it really serves an amazing purpose for getting the word out there that innovation is going to be key to managing water and infrastructure. So thank you.
Oh, you're most welcome. Well, I totally agree with you. Just kind of look at the options that water managers have today compared to 20 or 30 years ago. There's not as much water available, but there are more ways to get it and to stretch what you have. And so that's really going to be key going into the future. So thanks again. This has been Talk Plus Water, and my guest today was James Perry, Executive Vice President of ASTERRA. I also want to thank you, the listener, for spending your valuable time on this podcast. And finally, I want to give a big thank you to Anna Huff at the Meadows Center for Water and the Environment at Texas State University for getting each episode of Talk Plus Water ready to go. My name is Todd Bottler. Let's talk water again soon.